Okay, well, thanks everyone for coming. So today's speaker is Professor Paul Kwiat from University of Illinois at Urbana. So Paul is one of the pioneers of quantum optics. He did his PhD in 1993 with Ray Chow at UC Berkeley, and then a postdoc with Anton Zeilinger, and then stint at Los Alamos, and he's been at University of Illinois since 2001. And among the many awards he's been awarded, one of them is for the R.W. Wood Prize from the Optical Society of America in 2009 for being the primary inventor of the world's first sources of polarization entangled photons from down conversion. That's just one of the many contributions he's made to quantum optics. So it's a huge honor to have you here at our Q Farm. Please go ahead. And I just want to remind everyone that your questions, you should put your questions into the chat box, and we'll be monitoring them, and Paul will be monitoring them, and try to answer them during the talk. Thanks, Paul.
Thanks, everyone. Thanks so much for the invitation. I'm really glad to be here. I guess maybe coming from the Midwest, being at the Q Farm seminar was somehow moderately appropriate in some way. I will say one thing I always tell my students on the first day of class is that Kwiat is not quiet. Common issue. Okay, so let me just hop into it. So today I want to give an overview about how we can use multiplexing in order to improve single photon sources and quantum memories and things like that. And I do have a habit of always changing my title a little bit. And so my maybe more appropriate title is that this is going to be about temporal multiplexing and also, what will I say, a warning about the evils of loss in these kind of systems. Okay, so it's a brief outline of what I want to talk about. First, sources, and then memories, and then things I wish I had, and maybe there are people there who can help me get some of them at least. So a lot of this, this is just a snapshot of my recent snapshot of my group. I guess we all have these kind of Zoom snapshots now. And the work I'm going to be talking about today is primarily from a previous postdoc I had, Fumihiro Kaneda. And then that work was taken on by one of my students, Colin Nualdi, and then the quantum memory work is by Michelle Victora. I'd just like to say that Fumihiro is now in Japan, and Michelle is going to be graduating soon, so we are certainly looking for people to fill the empty spaces on our Zoom board. Okay, so single photon sources. You sort of have, I guess I would say, three main options. So one thing is you could just take an attenuated laser pulse, like from a laser pointer, a weak coherent state, and that certainly is very easy, and for some applications that is sufficient. So for example, for quantum key distribution, it can be sufficient to make a secure protocol, basically. But it's pretty much insufficient for many other applications in quantum information processing, and the primary reason, of course, is that we have Poissonian statistics, so that, for example, if we have a reasonable probability of having a single photon, let me get myself a laser pointer here. If we have a reasonable probability of having a single photon, then we also have a pretty high probability of having two or more photons. I can attenuate the whole thing so that I don't have those higher photon contributions very much, but then I also don't have my single photon contribution. So that's going to be pretty limited. Another option is I could have a single emitter, like a single atom or a single quantum dot, something like that. And that's going to be very good for not producing more than one photon. That means I have a low G2. In principle, they can be deterministic, but they do have the difficulty in that it can be difficult to catch that photon. Oftentimes, they need to be cryogenic. And at least in some cases, for example, with quantum dots, it can be difficult to get the different emitters to be identical to each other. So then the final option is going to be using a so-called pair source, where I have produced pairs of photons, and then if I detect one of those two photons, I know that I have another one. And that definitely can have some advantages. Move my chat box over here. Okay, definitely have some advantages in terms of getting great mode matching and high efficiency. They can operate at room temperature, but they are probabilistic, and we'll see that that can be a difficulty because that will cause them to sometimes be emitting multiple pairs. So let's just sort of understand the competition, let's take a particular example of a single photon emitting source, say a quantum dot. So this is a paper from John Ray Pan's group several years ago. And if you just read the items in the red, it sort of seems like all of our problems are solved. So there's a quantum dot that's in the middle of this vertical micro cavity, micropillar, and that photons that are emitted are primarily emitted along the cavity. And so they have quite good single photon purity. The photons look indistinguishable to each other at a pretty high efficiency, seemingly of 66%. But if you look more carefully in the paper, the actual rate that they get out is about 4 megahertz, and they're pumping at about 80 megahertz. So their actual efficiency is only something like 5%, or if you divide out their detector inefficiency, about 15%. Now, one issue is that they're pumping and they need to pump with one polarization and extract the photons with the perpendicular polarization so they can use a polarization filter. And because in this case, the photons had all polarizations, they ended up throwing away half of their light. That's now been fixed in a more recent technological development, but these still only have efficiencies, extraction of efficiencies of something like 60%. Let me just say though that they were able to use that device, so they have the single photon source on the left over here, single photon source on the left, and then they drive it many, many times, and then they have the switch yard, and they're able to do, in this particular case, a boson sampling experiment with up to 14 photons detected. And on the right, we're just showing that by changing how they're driving the photon source, they can control whether or not it's emitting photons. So they were able to get quite good G2 values with this, and by combining with the switchyard, they were able to do these experiments up to 14 photons, but that happened only at a rate of about 6 events per hour, which is not so good. The other thing as an experimentalist that I noticed in their system is that they have 19 Pockle cells in their switchyard, which is maybe even the sadder thing than having to wait 10 minutes to get one event. So let's see if we can potentially get around that. I do just have one other slide. This is from Pascal Selenard's group, basically just showing that these quantum dot sources have been certainly improving over time. And one of the original problems they had was that all of them, any individual quantum dot would look different from others, and they've been able to now, for example, get quite reducible performance between different quantum dots, between up to 15 quantum dots, with the indistinguishability of maybe 92% from each other. But nevertheless, they still have pretty low collection efficiency from the quantum dot into a single mode fiber, which is in some sense the metric that you really care about. You don't just really want the photons to go off anywhere, you really need them to go in some precise mode that you can then do things with. Okay, so the other option is to use a heralded source. So we start out with some mechanism by which we can have pairs of photons, so either through spontaneous down conversion or four-way mixing, where I take some pump photon or pair of pump photons, and then I convert it into a pair of photons. And if I detect one of those photons, called the signal, then that heralds the presence of the idler photon. And because the energy and momentum conservation is well controlled in these systems, this can really go into a well-defined mode. The one difficulty, though, is that this process is governed by thermal statistics. So this is the probability of producing K pairs per pulse, depending on the mean number of pairs per pulse mu, on the average number of pairs per pulse mu. And we see that the best that you can do, if you drive at an average number mu is equal to 1, the highest likelihood of getting exactly one pair is 25%. So if you drive weaker than that, then mostly you're producing no pairs. And if you drive harder than that, you're still actually mostly producing no pairs, and then some small probability of 1, and a not smaller probability of 2, and yet smaller probability of 3. But basically, the best you can ever do is 25%. So that's not seeming very good, because we'd like to get that to be as close to 100% as we could. So I will say as far as I know, the largest experiment that's been done using this sort of system was again by John Ray Pan's group in a different experiment. a different boson sampling experiment, a 12 photon experiment. And the way that they get their 12 photons is they have 6 sources here, and they drive them all, and they hope for the unlikely event that each of those sources emits exactly 1 pair. Now, of course, it's also equally likely that the first source would emit 4 pairs, and the next one would emit 2, and then the other 4 wouldn't emit any. But they need to look at the cases where each one emits just 1 pair. They certainly were able to take data, so you can see this lovely state characterization that they did. But unfortunately, because that process is so unlikely, they're working at about 1 event per hour, which is definitely an unhappy. So if you think about the fact that their plot here has about 300 data points, that means it was 300 hours. So it's a very long amount of time to just be able to characterize one source. So I would say that I wouldn't necessarily agree with their term that this is a scalable type of approach. Okay, so the solution is going to be to use multiplexing, and that will allow us to get something that's much closer to a deterministic source. Okay, so what does that look like? So if we take a normal heralded single photon source, and instead of just having 1 of them, I have a whole bunch of them, and I pump them all simultaneously, and I can monitor which one produces a pair by looking at the signal photons. I then know that, okay, I know that it was this source that produced a pair, and therefore I need to route that photon through some switchyard to the output. Okay, so if I do this with spatial multiplexing, I need to have many crystals, and I need to have many detectors, and I also need to have a low loss photon switchyard. And that's maybe not such an easy thing to get at the moment. So I'm instead going to talk about time multiplexing. So if I just take a normal of these sources and I drive it with a bunch of different pulses, time bins, I'm going to have a low probability that there's a photon pair in any particular time bin. I mean, I said I could get it at most to be 25%, but I really don't want to drive so that I have so many multiple pair events, so I'm going to drive it more weakly. That means most of the bins are going to be empty. But you could imagine, in this case, considering every 4 time bins to be 1 multiplexing cycle. And in this case now, I'm more likely to get a pair somewhere within those 4 cycles. And then if I have some way of switching between all those 4 cycles, so switching any of those 4 cycles into the same time bin, then I can get a much higher efficiency by doing this sort of time multiplexing. So in fact, this scheme was first demonstrated nearly 20 years ago by Jim Franson's group, where they had a down conversion source. They trigger on 1 photon and then they store the other photon. Now, unfortunately, at that time, their losses per cycle were pretty high, about 26%. So that means you can't go more than roughly, I don't know, 8 cycles at the maximum. And so that's not actually going to end up buying you very much in terms of helping out the efficiency. Okay, so we've set out something that's quite a bit more efficient. So again, we have a down conversion source. We're running it quite non-degenerately, which means that the triggering photons are at around 777 nanometers, and then the photons that the wavelength that we're trying to produce is at 1590 nanometers. And we chose those particular wavelengths because it allows our photons to be in fairly pure quantum states. There's some other reasons I can allude to later. So I'm going to detect 1 photon, and then I will store its partner in the storage system, and I'll go in detail over how that works a little bit later. But basically, we can store for an arbitrary number of loops, and this loop length at 10 nanoseconds is matched to the repetition rate of the pump laser that's coming in. And because we actually have fairly low loss elements, the Pockle cell and the polarizing beam splitter are quite low loss. In fact, we have something like a 98.8 or 98.6% transmission per loop loss. And that means that we can go for something like 40 loops in this system. So that's going to be a lot better than the original experiment that Franson did, where they could only go 4 or 5 or 6 loops. So this is just a schematic that has a little bit more information about how this is actually working. So we have a collinear PPKTP source, and we use a dichroic mirror to pull off our trigger photons. We have a cascade of detectors. Having more than 1 detector enables you to detect some events where you had 2 pairs that were being produced. And then the other photon gets put into the storage system. We also have a Pockle cell, and it's controlled by this Pockle cell here. This is also a Pockle cell afterward, so that if we happen not to get a trigger photon, if we happen to make a pair, but we didn't detect the signal photon, there would still be an idler photon here, but we wouldn't know that because we didn't have a trigger. And therefore, we want not to be trying to switch those out because we don't know that they're actually in existence. And so we have another Pockle cell that basically is going to dump out all photons except ones that are coincident with one of our detectors firing, and also with a pulse from the laser coming as well. Okay, that's shown over here with this photodiode. Okay, there's one other feature that's in here that makes it behave quite a bit better, which is this fiber delay. And the reason we have that is this basically gives us a 500 nanosecond buffer. And what that enables you to do is to produce, say, 40 time bins worth of photons, and to see what is the latest time bin that contained a photon, and only store that latest time bin. Because if you happen to produce photons, say, in time bin 2 and in time bin 38, the photons that are born in time bin 2, because there's loss in the storage system, they experience that loss for 48 cycles, whereas the photons that were born in time bin 48, they only experience that loss twice. And so you're much better off only working with the latest created photon, and that makes the efficiency of the scheme quite a bit higher. Okay, so how does all this work in our case? So this is first looking at the heralding probability. So this is the likelihood that we actually produce a pair somewhere within this number of time slots. So somewhere within 30 time slots or somewhere within 40 time slots. And then the different curves correspond to pumping harder and harder. So this is pumping quite weakly, and at the top we have about a 20% likelihood that there's a pair on average in any given pulse. And we see that when we run with this higher pumping, we're able to come very close to saturating this heralding probability. In other words, within these 40 bins, we have a 98% likelihood that we produced a pair and detected a pair. So we've detected the signal photon. Now, in terms of the actual performance of the source, it's going to be less because I am going through this memory and there is some loss in that memory. And so that makes the actual single photon probability, right. So this 97% or 98%, that's obviously much better than the 25%, which is the limit if you don't do multiplexing. Okay, so when we include the loss from the actual storage system, then these results go down, but we're still able to get a basically a 2/3 probability, a 67% probability of producing the single photon, and that's coupled into producing and collecting into a single mode fiber. Okay, so I think that that's the highest efficiency single photon source that I'm aware of at the moment, at least coupling into single mode fiber. So we could compare to some of these other sources. So compared to the down conversion source that I already showed you and the quantum dot source that we already discussed, and we see that indeed the efficiency into single mode fiber is quite a bit higher. The indistinguishability is comparable, but there is this issue that the G2 is quite a bit higher. And the reason for that is that at the moment, the experiment that I showed where we have this 4 detector cascade does not catch the number of events where we had multi-photon events. So because of the fact that we get this high efficiency only when we're pumping pretty hard, that means that we are occasionally producing 2 pair events and maybe also sometimes 3 pair events. And with the system right now, with this cascade of fairly low efficiency detectors, we just don't catch many of those. Okay, but we are now in the process of installing some very high efficiency superconducting nanowire detectors. which we hope will be able to have efficiencies upwards of something like 95%. And these devices have even been shown to have some intrinsic photon number resolution capability. So using some fairly realistic improvements to the source, we think we should be able to push the probability up to like 75% and the G2 down to something like only 0.05 and increase the rep rate by maybe another factor of 10. So to put that in perspective, let's say that we weren't just trying to produce one photon, but let's say that we wanted to have a whole string of them, just like what was done in the original Pan experiment where they had the quantum dot producing a whole string of photons. So you could ask, how many photons do you get out? How many times do you get, for example, a 10 photon event or a 12 photon event for these different sources? And for example, the red curve here, this is the one where they had 12 photons, but they had to wait a fraction of an hour in order to get that, or the quantum dot source. So if we compare instead our current existing source, we should have something like 10,000 12 photon events a second, and maybe even some 30 photon events a second. And that's without what I think are quite realistic improvements. So we should be able to get really a much better performance out of this, hopefully in the relatively near future. Okay, so that is a good thing. So we're pretty happy about that. Of course, in this area of COVID, keeping your mouth open is maybe not such a good thing. So we need to be mindful of other constraints on the source. So it's not quite all roses as we might like it to be. So one issue is this rate. So I said that we're running at about, right at the moment, at 500 kilohertz, and these other sources are running at about 80 megahertz. So why is that? Basically, we're entirely limited at the moment at how fast we can drive this bulk Pockle cell that we have. It takes about 3,000 volts to switch the polarization, and our driver can only do that at roughly a megahertz. So there has been quite a bit of recent work, particularly from Marco Lonkar's group, using, for example, thin film lithium niobate, and they've been able to get modulators that are extremely fast, with a relatively low optical loss on the chip of only half a decibel. Although even that is 11.5% loss. And in fact, in their system, if you read more carefully in the paper, they had an insertion loss of about 5 dB per facet per end of the device. So that's actually not going to be very useful in our particular application. So let's just talk about the effect of loss in this system. So this is how we currently are doing, and we have approximately 1% loss. But you see that the performance drops really quite markedly as soon as you get even 5 or 10% loss. And 1% loss is going to be quite difficult to get in maybe an integrated optic device, because of course it'd be much better to be able to do this whole thing in a small waveguide device, maybe, instead of in this setup that's on our optical table. The other issue is that if you go through another device like a waveguide device, you might have a difficulty with dispersion. So in particular, if there's dispersion in the system, and maybe we also have that, so we need to look and see whether that's the case. The reason dispersion would be a problem is that as your photons are going through the storage system, if there's dispersion, those pulses are going to be getting wider, and then the width of the pulse would depend on how long you're in the memory. And that's absolutely not what you want. You want your photons to be identical, irregardless of how long you've had to store them. So let's just see in our particular example whether that's true. And in order to do that, to test that, we've compared, we've done a 2-photon interference experiment between photons from our time multiplex source with photons from a non-multiplexed heralded single photon source. And I'll make a long story short and just say that we get high Hong-O-Mandel visibility, high 2-photon interference visibility, kind of no matter how hard we drive the system. If we subtract off accidentals, we always have something like a 92% visibility. So what that means is that when we're going in our storage system, whatever dispersion there is not high enough to be wrecking the indistinguishability of the photons as a function of how long they're in the storage system. Okay, I think before I go on to quantum memory, I will ask if there are questions in particular. Going once?
Well, I had just a question about the experiment you showed. So what were the round trip losses there for the buffer?
Yeah, our round trip losses were about, in this case, 1.5, 1.6%.
Okay, thanks.
And that's mostly in the Pockle cell and in the polarizing beam splitter. Right, so there's another question about when will, that we're doing work on trying to improve this, when will that come along? So we are currently waiting on new detectors from Quantum Opus. Unfortunately, the pandemic really slowed a lot of things down, so that's one issue. We're also installing a new Pockle cell, but it requires some water cooling. So it's kind of an interesting thing. So we, of course, have water cooling on our driver, but it turns out when you run the Pockle cell fast enough, there's a little bit of thermal distortion in the Pockle cell itself. And because we're having extremely good mode matching into our optical fiber, at the end, when there's a little bit of thermal distortion on the Pockle cell, it turns out that you no longer get our 99% coupling into the single mode fiber that starts to drop. And so we're installing some other water-cooled Pockle cells, and again, things have been slowed down a little bit, but I'm hoping that by the end of the summer, we'll be able to have some of those other improvements in place. The pulse duration, that's a good question. These pulses are, I believe it's about 300 femtoseconds. And maybe I'll do the last one, let's see. How many photons, modes of photons would be accessible before the jitter and mode mismatch becomes an issue? I think by jitter, you mean the maybe the dispersion impacts. I'm not exactly sure. Lots of things coming up here. So, so I think that I don't have I guess I don't know the answer to that because we're not doing it in a fiber network. I will say in principle, you could do dispersion compensation mechanisms where you have positive and negative dispersion canceling each other on each trip. There's absolutely no reason you couldn't do that, except for the fact that a lot of times those involve extra loss. And since we're trying to keep the loss really low, we're just fighting a kind of a hard battle that way. The power of 0.18, I actually don't know. I'd have to look at the paper to determine that. It's not the hardest that we could drive. We could certainly drive it a little harder, but I'm afraid I don't know the answer. The length of the optical delay in the loop is 10 nanoseconds, so it's 10 feet because it's matching the rep rate of the laser. And lastly, and then I want to move on to memories. How does the indistinguishability, I'm trying to scroll down here. How does the indistinguishability of two independent sources compare with two independent quantum emitters? Yeah, it really depends on the quantum emitters. I'll just say that they're comparable. I mean, we've seen comparable results. Some of the two independent quantum emitters have also seen around 93 or maybe 94%. The results I showed also were without filtering, and if you put some spectral filtering in, then you can get it better. And the other thing is the source I showed, the periodically poled source, is not the best that you can do in terms of getting more spectrally indistinguishable photons. You can use a source that's not periodically poled, that has an aperiodic polling, and we've been able to do that and push the indistinguishability up to something more like 97 or 98%. But that happens at the cost of the efficiency of the whole thing. And then we do start to run into a situation where we're not able to drive it quite hard enough at the moment. But I think that those are definitely fixable problems. Okay, so let me move on to quantum memories here. Thank you very much, by the way, for all of the questions. Very good questions. Okay, so of course there are many reasons you might want to have a quantum memory. I mean, in a quantum computer, presumably you need one to synchronize things. And also, I've been thinking a lot about quantum networks recently, where you have these Bell state measurements. That's just the same sort of thing I just showed, a Hongo-Mandel measurement, where you combine two photons on a beam splitter, but you only get the benefit of sort of hooking together a bunch of these if you have quantum memories so that you can synchronize different parts of the network with each other. So that you're not just driving a whole bunch of sources independently and hoping that you get a pair out of each of the sources simultaneously. If you have to do that, then you're down at the same problem that we've already had. Particularly if there's loss in the system, because even if each of the sources is deterministic, if there's a lot of loss transmitting the photons, then you still end up equivalent to just trying to send the photon over the whole channel. So you really need to have quantum memories, multi-mode quantum memories, in order to boost up the efficiency of these schemes. So, okay, there's obviously many types of quantum memories that people look at, and this is in no way meant to be a comprehensive picture of all of them. I've just highlighted sort of two of the other ones. So one of them is based on atomic ensembles, for example, where we have electromagnetically induced transparency-based memories. Another one might be based on atomic frequency combs in some sort of a solid state device. And the main thing I want to highlight with these, because they all have different performance characteristics in terms of what the storage time is and what the efficiency is, and whether you have to cryogenically cool them, things like that. But the one thing they do share in common is they tend to not be very broad bandwidth. And I will come back to that in a fair bit as I make the comparison with our approach, which is actually just using an optical delay line. Okay, so I didn't really go into detail before about how this works, but I will now. So assuming that we had an input vertically polarized photon, I then use my fast switching Pockels cell to switch it to horizontal polarization. It's transmitted through this polarizing beam splitter until I fire the Pockels cell again, changing it back to vertical. So depending on when I fire the Pockels cell, I can stay depending on when I fire the Pockels cell, I can stay as many loops in the system as I want to before I fire the Pockels cell again and then launch the photon out. So I'm going to be showing some data here, and that data is going to be taken, in this case, with a slightly different system than the one I already showed you. So in that case, we're trying to match the rep rate of an 80 megahertz laser. So the pulse loop length is 12.5 nanoseconds. Okay, so there are some benefits of using an optical delay line. One thing is that it's controllable. So for example, some of the quantum memories you can store for a long time, but you can't adjust how long that amount of time is. So it's sort of just like a fixed optical buffer in some cases. We also have a capability of storing multiple modes, as shown by the fact that I could store for 1 loop or 2 loops or 27 loops. And also, as I'll come back to, we have a pretty high, actually an extremely high bandwidth. But there are limits, which is that it's hard to get a very long storage time, as I'll talk now. So in this particular experiment that we've been doing, the loss in our Pockels cell is a little bit higher. It's about 3% between the Pockels cell and the polarizing beam splitter. So if I want to go anywhere from 1 to 20 cycles, I can do that. Even at 20 cycles, 0.97 to the 20, that's the total loss I've experienced, still gives me a transmission of about 54%, which is not too bad. But let's say instead of 20 cycles, I want to store 537 cycles. Okay, well now, 0.97 to the 537, this is essentially 0, so it's 10 to the minus 7. So basically, this is not going to be possible to store for an extremely long amount of time using this kind of system because of the loss in the switch. But we can play a trick where we can combine optical loops, optical delays, optical memories of whatever kind. At the moment, I'm going to be talking about these optical loops, but it could be different types of quantum memories as well. But in this case, let's look at this digital system where I have one delay, which is 12.5 nanoseconds, another delay, which is 10 times that, 125 nanoseconds, and a third delay, which is again 10 times longer than that. So now if I want to store for 537 times 12.5 nanoseconds, the way to do that is I store 5 times in the longest cavity, 3 times in the middle cavity, and 7 times in the short cavity. In doing that, though, I've only had to go through the lossy switch 5 times for the longest cavity, 3 times for the middle cavity, and 7 times for the short cavity. So now the net transmission is about 63%, which I think we will all agree is a heck of a lot better than 10 to the minus 7. Okay, so being able to do the stacking is going to greatly improve the storage time. I will this extra caveat that this is assuming that the loss is dominated by the switches. If instead your loss is dominated by how often you're bouncing off the mirrors, then going to longer and longer times where you bounce off more and more times, of course, is going to hurt you. Okay, so we have set this up over quite a few years in my laboratory, it turns out. And I can move my chat windows so I can see what I'm doing here with my laser pointer. Okay, so the photons come in, and the shortest loop, 12.5 nanoseconds, is just a 12.5 foot loop, actual loop on the system. And then we come out of that, and the photon is horizontally polarized. And if I leave it horizontally polarized, I will not go through the second loop. But if I switch it to vertical polarization, my photon will be reflected here. It'll go through this 125 nanosecond delay, and then it'll come back, still vertically polarized, and I can keep going through that delay as often as I want. And if instead I want to switch out, I'll make the polarization horizontal, and I'll now switch into, switch the polarization again to vertical, and now I'll be switched into this longer loop, this 1.25 microsecond loop. And again, I can go through that as many times as I want until I switch the polarization again, and then the whole thing gets switched out. Okay, so there are 2 sort of interesting memories here. The shortest one is not interesting. It's just a loop with some lenses to keep the mode the same size. Whoop. Sorry, I have somehow exited my talk here. There we go. Okay, so the middle loop, the 125 nanosecond loop, that's made with the so-called Harriet cell. I have 2 spherical mirrors. Each of them has a hole in it, and the light bounces back and forth, sort of in a Gatling gun pattern. I think it's roughly 19 cycles before it leaves by the other hole. And then the 1.25 microsecond, so that's actually quite a bit more challenging. You can't do it just with spherical mirrors, because with spherical mirrors, you can only get an elliptical pattern, and the spots get too close to each other. So instead, what we have is a so-called modified Harriet cell, where I have 1 spherical mirror and I have 2 flat mirrors, but the flat mirrors are tilted slightly with respect to each other. And what that gives us is a kind of a complicated Lissajous pattern that really fills the surface of the mirrors. So because now you're limited by the area and not just the circumference of the perimeter, you can have a lot more spots, in this case, roughly 200 spots. And the photons come in under 1 mirror, and then they leave over the top of the other mirror. Okay, so we've taken a fair amount of data with this system, although there's still work that's ongoing. So this is just looking at the losses or the efficiency of each of both the short loop and the middle loop and the long loop, and getting a sense of how much loss we have per cycle in each of those loops. And then on the right-hand side is the data showing going everywhere from 1 to 999 cycles of 12.5 nanoseconds through the system. And you see there's this sort of interesting scallop that happens. So for example, at this data point here, we've gone 9 times through the short loop and 9 times through the middle loop and no times through the longest loop. And that's pretty inefficient, going through those short and middle loops so many times because of the loss in the switch. So if instead you go through them, you only go through the long loop once, then the efficiency jumps back up again. And in fact, there's also, if I were to spread this out in time, there's also a scallop that occurs every time you go from 9 times in the short loop to 1 time in the middle loop. Okay, we've also been coupling into single mode fiber, and at least for the first loop and the second loop, we're still able to maintain fairly good transmission in this case. We're still working on the transmission measurements for the third loop into single mode fiber. That was another casualty of COVID-19 for the moment. But anyway, we started that work up again. So you could ask, well, how good could we actually do in this system? So currently our Pockle cells have have losses of, let's say, 2 or 3%, along with similar a percent or two on the polarizing beam splitter. And the mirror reflectivities are about 99%. But it's possible to have Pockle cells that have transmission closer to 99% and mirrors with 5 nines of reflectivity. So if we just theoretically put that into a model of what our efficiency could look like, we actually could get a system where we could store out to something like 100 microseconds in 10 nanosecond steps or 12.5 nanosecond steps, with a really quite high efficiency. I will say one other quick thing, which is that we're doing things in base 10. Base 10 is not the most efficient scheme. The most efficient scheme would be to use base 2, so that you, instead of having to go through the switches multiple times, you'd only end up going through each of the switches once. So for example, to go 1,000 cycles or 1,024 cycles, you'd need a total of 10 switches. You'd always go through each switch once, but you'd never go through more than 10 switches. Whereas in our particular case, with a digital system, if you want to go up to 1,000 cycles, you might need to go through each of the switches 9 times. So you might need to go through 27 switches. And so that ends up not being quite as efficient. Okay, but it's a lot cheaper to have 3 switches instead of 10. Okay, since I want to use this for quantum information processing, I want to ask, how can we actually store quantum bits in this system? So let's say I have a polarization qubit and I go into my system. Well, we see there's an immediate problem because only the vertical component is getting stored and we're immediately switching out the horizontal component. So that's not going to work. Instead, we want to convert the polarization qubits into time bin qubits. And here's how we can do that. This is a quantum transducer where I take a polarization qubit state. I'm going to go on to polarizing beam splitter. The horizontal component will take a short path. The vertical component will take a long path. And then I'll combine these again on a polarizing beam splitter. And now I use a Pockle cell to rotate the polarization of the later pulse, the vertical pulse, to make it horizontal. And then I can switch into my quantum memory. When I come out of my quantum memory, I can go back through the same system in reverse. It turns out there's a switch that's happened where I've switched what previously went the short path now goes the long path and vice versa. That's nice because it makes the whole system stable if there are any issues with vibrations or path lengths changing inside of this long path. But nevertheless, that means that our transducer is going to operate like a sigma X operator, like a flip operator. And then we can do a tomography of the photons that come out. Okay, so we've done this. We've characterized this by using process tomography to characterize what kind of quantum state we were expecting. And this is what the process matrix for this sigma X matrix should look like. And then we'll compare what are our actually measured chi matrices, that's what these are called. How do they compare with the ideal chi matrix that we expect? And these are measurements taken on our short loop for different cycles through the short loop, and we have roughly 98% process fidelity. And these are measurements taken on the middle loop. We have not yet taken the measurements on the longest memory yet, the 1.25 microsecond memory yet. So one thing I'll point out, again, we have about 98% efficiency. But remember that when I'm making this measurement, I'm going through a transducer first, and then I go through the memory, and then I undo that, I go back to the transducer. So you might wonder whether that 98% is really due to our memory, or is it just due to the fact that our transducer is not perfect? So the way that we can determine that is we can just not go through the memory at all. We can just go through the transducer and then basically go right back into the transducer the other way again. So basically just measure this T inverse T, and we'll compare that to what we had here. And that will give us a sense of what our actual memory is doing. And when we do that comparison, in fact, we get something like a 99.8% fidelity between the double transducer with and without the memory. And so that means that our memory is extremely close to being the identity matrix, which is great. Okay, I've commented in the beginning about other quantum memories having a pretty narrow bandwidth. So in our particular system, our laser is tunable over something like a 1.5 terahertz bandwidth, which is far more than other quantum memories that I was talking about. And the fact that we can store for something like 4 microseconds up to 50% efficiency means we have a time bandwidth product that's about 6 times 10 to the 6, which is orders of magnitude more than any other quantum memory that I'm aware of. And this basically effectively defines the maximum number of pulses that you could store in the system. In fact, the theoretical limit for our current system is limited by the Pockle cell operation. And that actually has a bandwidth of something like 70 plus or minus 80 nanometers. And so we, in principle, get an extremely, extremely high time bandwidth product for this kind of system. I will say, though, that in practice, our switching repetition rate is again limited by how fast we can fire these Pockle cells. So that's, again, a nemesis for us. We're working on seeing if there's a way to get that the system that could switch at much higher rates, but that's definitely something that's still in progress. Okay, so in this memory case, we've been able to get transmissions quite high, even up to 5 or even 10 microseconds with very high process fidelity for the memory itself. And we've also been able to implement a quantum transducer that has a quite high process fidelity. Because of the fact that these elements all have quite high bandwidth, that leads to an extremely high time bandwidth product. And we're currently trying to finish our data with our third loop so we can do fiber coupling and then also get process tomography for that. And the one other thing I want to say is we've talked about storing polarization qubits. We do that by converting them into time bin qubits. So we know that our system can already store time bin qubits. And because it's in free space, it's possible that it might also be able to store quantum information stored in orbital angular momentum modes. You, of course, then wouldn't couple into a single mode fiber at the end, but in free space, you might be able to. And that's something else that we'd definitely like to measure. And then let me also comment that although our total memory time is limited to maybe 100 microseconds, there is a potential for using a hybrid quantum memory where you would add this onto another slower quantum memory that wasn't switchable, but that had a much longer lifetime. So maybe for example, an atomic ensemble memory that might have a millisecond storage time could then be combined with that, with this sort of system to add depth to the quantum memory. Okay, so my last slide is actually only one slide long, so let me just do that and then I'll ask for questions of things I wish I had that I don't related to this topic. So it would be great to have very high efficiency, low jitter, photon number resolving detectors that weren't cryogenic like the superconducting detectors, because basically because they're extremely expensive and not that easy to work with. I would love to have some sort of an integrated ultra low loss, very fast switching, high rep rate optical switches basically. It would be great to have a heralded quantum memory. So everything I talked about was not a heralded quantum memory. We don't actually know when our photons go in unless we have some other signature saying that the photons are going in. So for quantum repeaters, it's much better to have a heralded quantum memory. Everything I've been talking about has been producing deterministic single photons, not entangled photons. And the world is really lacking a deterministic entangled photon source. And I could talk a little bit more about that, but basically, let's just say I don't think that there are any really good options for that at the moment. So that's a bit of a problem. And as long as I'm being, having wishful thinking here, having a quantum non-demolition detector that could determine whether photons were present without collapsing their quantum state would also be extremely nice, because that would convert, for example, our quantum memory into a heralded quantum memory. And it would be useful for many other things as well. Nevertheless, I can end with a fairly conservative prediction, which is that multiplexing of one sort or another, I think will definitely play a key role in pushing together the quantum revolution. So with that, I will quote Einstein, which is always a good thing, although given what's happening in our country at the moment, maybe a more appropriate message is that we should not stop social distancing. Okay, with that, I'm happy to take questions.
Thank you. Well, I guess here's your virtual applause.
Thank you.
Yeah, thanks for a clear talk. So yeah, I guess questions. Mark had a question actually.
Yeah, so
Mark, maybe I can even unmute him.
Great.
Okay.
Hey, Paul, thanks a lot for the talk. This is really great. So I'll just read my question. I, and I think many other people, consider you to be a leader in these experimental efforts. When do you think you'll have a usable, like, quantum internet? I'm doing the final proofreads on Dowling's posthumous book, and he said 10 years, but he was always optimistic.
So I guess I would say I think that is somewhat optimistic. It depends a little bit what you mean by a quantum internet. So I think there are a couple issues. One is how long does it need to be in terms of what's the distance need to be, and the second, of course, is what does the rate need to be. So I think it's entirely likely that within 5 years we will have quantum repeater enabled links that can beat the so-called repeaterless repeaterless threshold, so that you'll get a higher probability of sending quantum information than the probability of transmitting the photons that carry that quantum information. So I think that's probably within 5 years. But that's, that's getting one or a couple repeaters, and to go long distances, you need to have multiple, a lot of quantum repeaters. It's not unlikely to me that we might end up with sort of short quantum local quantum networks, which may be then initially connected by entanglement bridges, for example, by satellites. So for example, if you want to connect Europe to the US, probably almost certainly the fastest way to do that is by putting a satellite in orbit and sending entangled photons down to the 2 ground stations. Of course, maybe that only works in the satellites overhead, but at least it does seem encouraging that you might be able to get reasonable rates for that. So I think that that's possible. Yeah, I guess I'll leave it at that.
So for the satellites, do you have a prediction? Do you want to be so bold as to make a prediction there?
Well, I mean, there was an article in Wired magazine, so I'm allowed to at least quote that, I don't know, a couple months ago, that NASA is definitely looking into this pretty seriously right now, and I'm on a couple other NASA panels that are looking into this really quite seriously about trying to see what would it take to be able to make an entanglement bridge. There are some big challenges there, because you need to do you need to not just distribute the entanglement, but you need to do teleportation between a moving platform and a stationary platform. And that has not been done in any experiment at all. So although the Chinese experiment, the Mischius satellite experiment, did do teleportation, they did sort of the teleportation they did had all the sources on the ground right next to each other, and then they just sort of send the 1 photon up. And that was certainly it's the first time anyone had done that, so kudos to them for doing it, but it's not really useful teleportation. You really need to do it between a moving platform and a stationary one, and that's a much bigger lift.
Okay, thanks.
Sure. Speak to the possibility, advantages, disadvantages of doing temporal multiplexing of heralded single photons on an integrated platform. Right, so one huge advantage is that our system, is taking up a fair fraction of an optical table. It's pretty big. All that mode matching, you have to work really quite hard to keep it. And so that's a bit of a pain. If you could do everything on an integrated platform, all your modes would be sort of naturally matched, and that would be great. There are, I think, at least two difficulties. So the first I've already alluded to, which is loss, which is as soon as you have maybe 5% loss going through one of your loops, 5 or 10%, then you very quickly start losing the benefits of multiplexing. The second thing is that we need to do you're not going to be able to get very long loops on an integrated platform. That's not necessarily intrinsically a bad thing if you can run at a much higher rep rate. But now the problem is that we need to do some sort of a feed forward system. So I need to detect when with my one photon, with my trigger photon, when it is, and I need to use that control to switch on the other side. And the detectors typically have a latency of maybe at least a nanosecond or something like that. So even a nanosecond on an integrated platform is maybe not that easy of a delay, of a controllable delay to get. So that's a second issue. And then the third issue is the one I mentioned with dispersion in the system. So you need to make sure you work in some way where going through the system 3 times does not look any different than going through it 30 times. I guess I will say, if I were going to do things on an integrated platform, the better way might be instead to do spatial multiplexing, where you had a bunch of different sources, and then you still need a switch yard, but you don't have to worry about this dispersion effect so much, because in the switch yard, everything can go through the same distance on the integrated platform. But then you also need a lot of detectors, so that's another issue. Let's see. Can I comment on routes to deterministic sources of entangled states? Yeah, so there are, there are multiple ones. Let me just comment on 2 of them. So there are experiments that have been done using quantum dots, where you excite the quantum dot to an excited level, and there are 2 ways that it can decay, 2 paths that it can decay, and one has, say, one polarization, one has the other polarization. And you then end up with an entanglement between the state of the quantum dot and the state of the photon. And you can use that to produce entangled photons, basically. The challenge with that, in some ways I really like it, because when you excite the quantum dot, then you produce one entangled pair. And so that's nice. The challenge is that now I have to couple both of those photons out, and we're already having trouble coupling one of them out. So if at the moment our efficiency of getting one photon out and into single mode fiber is 30%, the chance of getting both photons out is only going to be something like 10%. And then that's no longer deterministic. The other option is that there are optical circuits, probabilistic optical circuits, where if you have deterministic single photon sources, you can drive one of these systems with a bunch of ancilla photons, and I think you need at least 5 or 6 of them. And then when 4 particular detectors go click, you know that in the other 2 output modes, you have an entangled source. So that's possible. That gives you a heralded source, and then you could combine that with this sort of memory. But again, the efficiency there is not very high. I think the best probability is something like 15%. So that means you need to do this, again, pretty often. So I think that's one reason I said that I don't really see great sources of entanglement at the moment. Another option, for example, is you could use a superconducting qubit system, where you can make good entanglement between superconducting qubits and microwave photons. But now I need some very good optical transducers to go from microwave to optical. And it's entirely possible that we'll have those in 10 years or something like that. But the best efficiencies I know of at the moment are still extremely low. So it's problematic. How would I compare time multiplexing with frequency multiplexing? So frequency multiplexing does have some benefits in that you don't have these long delays. That's true. Although typically that frequency multiplexing, in order to get it to work, you need, for example, they do some frequency shifting using different pump lasers. And so for every frequency bin, you might need to have a different frequency laser that you're using to do the transitions. So that's one issue. The efficiency has not yet been as good for doing the switching. So I don't know of any frequency multiplexing scheme that has the 98.6% efficiency that we're able to get. Which doesn't mean you couldn't get that. It just means that at the moment they haven't got that yet. But it's certainly extremely interesting, and it's entirely likely and maybe probable that the optimal scheme is a hybrid where you combine some level of time multiplexing, some level of spatial multiplexing, some level of frequency multiplexing to get the optimal performance depending on what you need and what the application is. Any other questions? Maybe I'll stop sharing my screen so at least I can see a little bit.
Maybe I can just ask kind of a naive question. The on the entangled source, are there schemes that use sort of a third order nonlinearity that could do that, or is it
so I think what you're asking is not, are there schemes that use four-wave mixing and 2 pump photons to get a pair? But I think what you're asking, are there schemes where you use 1 pump photon, you get 3 photons out, and 1
exactly
is a herald, yeah? So people have talked about that, but unfortunately the efficiencies are extremely low as a method of getting it. So in principle, it's certainly, in principle, there's no problem at all. If you just write down the equation, it's fine, except for the fact that chi3 ends up being an extremely small number. And maybe there are ways of enhancing that using cavity enhancements or something like that. That certainly is something that should be looked into. Or even ways of enhancing it using coupling to some atomic system near resonance, or using some other mediated interaction to push up the efficiency.
Okay. Well, if there's no more questions, I think we should thank Paul again for this great talk. So
thanks, everyone. Very fun. Nice to see some of you again.
Yeah, it was great to see you again too. So thanks a lot. So I'm gonna maybe end the recording then. And,
great.
Here we go.